Thank you, first of all, for the invitation. This is what I'll talk to you about today is a project that we've been working on for a couple of years and is still ongoing. So it's kind of a midstream report. And you can see here it's got a number of collaborators, the key ones being at the Fish and Wildlife Service and here at UNM, where a couple of my students are responsible for a good amount of the work you're going to see today. So Rowan Converse is a doctoral student here at UNM that's been supporting this project heavily, and then Mohammed Sadoun was able to come to UNM on a Marshall Plan fellowship and work in my lab for a little while, and did quite a bit of some of our analysis on this as well. So. And Steve Sesney and Grant Harris, for those of you that don't know them, they may not know it, but they're part of our community, and they're downtown at the Fish and Wildlife Service office in the government building. So this project started a couple of years ago with, as many projects do, with Steve and I having beers around a campfire and talking about the potential for automating waterfowl surveys. And so for those of you that aren't familiar, the U.S. Fish and Wildlife Service spends a great deal of resources monitoring waterfowl, their species and their counts on all of their refuges. And they do this by either driving a truck along the side of a water body and usually banging on the side of it to get the birds to fly. And then in the 15 seconds between when the birds leave the water and when you can't see them anymore, they say there's 1,000 of those, or there's 500 of those, or there's some number of those. And after you've been doing it for a while, I'm told you can get pretty good at that. And then the other way is from the air. As you can see here, they use, there's a whole fleet of manned aircraft that are maintained by the Fish and Wildlife Service specifically for this purpose, to fly over water bodies. And they, in this case, use the plane usually to spook the birds and count them. So there's usually a trained biologist in the rear of the aircraft who is making counts of those waterfowl. And so as you could imagine, no matter which of those processes you're using, there's a lot of potential for error, both in terms of what those people are able to actually see in that period of time, and then because these are all being reported manually by different folks all over the country, there is not a primary data record other than what that biologist wrote down. And so the potential for taking an aircraft and automated interpretation approach seemed pretty clear to me. And we now can collect image data, sub-inch very affordably. And there's a lot of good convolution neural networks that are publicly available, mostly from the big social media companies and tech companies in Silicon Valley at this point. And so we decided that we'd start down that road. And just before we dive in, this is how I'm kind of thinking about it. And so this figure that you'll see here will move up to the top left of the screen. And so you'll be able to follow this figure in terms of where we are in the process. So the core of it is we fly data. We have to label a lot of examples of that data. And as we'll talk about, we've tried doing that from crowdsourcing applications. We've also got some experts to do interpretations of that data. And then we use those known labels to calibrate neural networks and to label the rest of the image data. And so it's these three steps at its core, and we're going to spend most of our time in 2 and 3 today. So we flew quite a bit of imagery. Mostly the imagery you're going to see today is from Bosque del Apache. These data are quite literally irreplaceable at the moment, not just because the waterfowl that were there are not there anymore, but because there's a DOI ban on operating drones over federal land. And so these are the last data that anyone's going to see until that ban is lifted for Bosque del Apache. And so we're actually starting to work off refuge and not on federal land to continue prototyping this project while DOI figures out what they want to do with drones. So we collected, as you can see here, almost about 3,000 frames of data. And if you look there, you can kind of make out, those are some sandhill cranes there, the big guys in that image, and the smaller ones are various forms of ducks. And so this is the kind of imagery that we're getting. You can see it's a very complex background environment. For anyone who's paid attention to efforts in this direction so far, all of the work that's been done on this so far are, snow geese sitting on black water, or birds sitting on a white snow background on the Alaska coast. They tend to be what Strahler would call simple scene models, where there's a single object with a very high contrast background. What we're working with is real world data, where there's a lot of scene complexity and a lot of objects that look like birds that aren't birds, that even our expert biologist interpreters sometimes had trouble with, clumps of dirt that start to look like a duck. So we got all that imagery. You can see there's quite a few different altitudes that were flown and ground sampling distances accordingly. And this is really because we wanted to test out a variety of scales, and we were at the same time evaluating what altitude spook ducks. It was a strange experience. I just got done telling you that the primary way that they count waterfowl is by scaring them with a plane or by banging on the side of a truck. But they were very concerned, the service was very concerned that we might disturb the ducks with our aircraft. So we flew at several altitudes to find out what altitude they were scared at. Turns out 30 meters is about safe. Below that, it gets a little sketchy. So we started out, we took a lot of those data and downsampled them to 13 representative frames that had all the species, primary species in them that we wanted to see, and that represented a range of cover types from Bosque del Apache. And we had 18 biologists from the Fish and Wildlife Service label those data through the label box platform. So you can see here, they see an image, they go in and draw polygons around these birds. And we had them do that for the 8 dominant classes of waterfowl that are in the scene. And so those 18 fish and wildlife biologists were generated a little under 20,000 labels. So that's 20,000 individual birds being labeled. But you have to keep in mind that that's redundant by about 18x, right? So that's 18 people identifying the same birds. And we also have been collecting a series of crowdsourced data sets. So first, we were working in the label box environment. And so from January 2020 to May 2021, we were able to collect about 21,000 labels from the crowd. We have switched over as of May 2021, thanks to Rowan's efforts, to a platform called Zooniverse, which, in addition to being a labeling platform, has an entire crowdsourcing community that engages with it to collect those labels. So in that period of time, obviously a lot less time, we're already at about 185,000 labels, and tomorrow it will be a lot more. They're chugging along. And for those 2 data sets, we have 592 images that are in that training set. And so those are 592 independent frames that are in that training set, where they are being asked to label those waterfowl, sometimes redundantly between labelers, because we want to be able to get a sense of how quality individual labelers are. but the platform handles and is set up for this purpose. So once we achieve a certain number of labels on the same image, a certain number of times it's been labeled, then that image gets retired. So I believe it's 10. Once we get to 10 labels on an individual, not 10 individual labels, 10 times that an image has been labeled, then they move on. For all of those, we only did 3 classes, duck, goose, and crane. And part of that was based on feedback from users working with our initial crowdsourced system that said it was too overwhelming to identify the individual duck species when that's not your training or your expertise. Whereas duck, goose, and crane are fairly easily distinguished just because of their morphology. They're so different in size and shape. And from a management perspective, the Fish and Wildlife Service is mainly looking for individual counts to understand how much food they should be providing to those ducks. And so that could mean that they're flood fields to push the seed bank and insects up out of that field so that the ducks can eat that, or it could mean that they knock down a cornfields so that the corn is available for consumption. And so this categorization actually works quite well for them, because in terms of how much food it consumes, a duck is basically a duck. But a crane and a goose is as you can imagine, eats a lot more. And so they need to understand that difference. So the questions I'm going to show you some results on today are here. We wanted to know which classifiers work for this and how well. And then we wanted to start understanding how reliable those crowdsourced data are for producing these types of image labels. So this study's already out, or is in press, I should say. It hasn't been released yet. This is Sadoun's work, and he looked at 3 different machine learning methods, the most common architectures out there in the cat labeling world, YOLO, RetinaNet, and faster RCNN. They're all convolution neural networks. They're all they're similar architectures in the sense that they all fit in the same family of convolution neural networks, but they take a slightly different approach to that and are different iterations of this. So YOLO stands for you only look once, and is probably the most prominent and widely used system out there. And then you see a name like faster RCNN, and then I don't know if next year it'll be the fasterer RCNN or what, but that is literally a shortcut RCNN. So these are the 3 dominant ones at the time of this work, and which was about 1.5 years ago now. And we tested 3 class structures for that. Single class, meaning just detect, tell me if there's a bird or not. 8 class, where we had all of the individual species, and then that 3 class combination where we group the geese and the ducks to form duck, goose, crane, everyone's favorite childhood game. And so it turns out that YOLO is the best performing of those 3. So they were all exposed to the exact same data set. They were the exact same training labels, and the exact same validation labels were used. Those validation labels were randomly selected prior to anything being used for training. And all of those validation labels are from the expert data set, right? So these are the biologists' labels. So we distill their 18 labels down to a single master set of labels that we consider to be our best estimate of the identity of each of those objects. So for what you see here is that as we add class complexity, we actually lose the ability to do detection itself. So if you look at one class, and this is a little tricky, it's not like regular raster-based validation, because we have we can have a lot more objects. There's no limit on the number of objects. It's not a one-to-one mapping of pixels being labeled. We could have an infinite number of objects, and then we have a validation set of a known number of objects. But so we can get commission error where we have labels that are more than we would expect, which you can't have happen when you're dealing with pixels. So if you look at the graph on the right here, this is an attempt to visualize that phenomenon. But the headline here is that if we group all of the waterfowl together, then we can do much better at identity, I mean, just identifying any bird, than we can if we try to have more complex class structure. And so with the 8 classes, you can see our total classification accuracy really bombs out, comes below 50%. Now, this is a very small number of labels for these types of algorithms. So I wouldn't say that that means we can't do class-based classification, but this general pattern continues to hold true. As class complexity increases, our ability to detect the object, just to say that there's some kind of waterfowl there, goes down because we have more, a lot less samples of each one. And so there's a lot lower confidence in finding any given bird as being a bird. And so you see the accuracy declines from 98% for a single class, 86% for 3, and really bombs out once we expose it to the 8 classes. We do have commission error, places where we are identifying a duck where there isn't one, and usually those are big clumps of dirt. We also have omission error where we're missing ducks, so that's indicated by the percentage at the top, right? So we labeled 80% of waterfowl in the image. Well, that means we missed 20% of the waterfowl that were in that image. Okay. If you look at RetinaNet, it does very similar pattern, but just a little bit poorer classification quality. And same for faster RCNN. And this is the only method that had a lot of trouble with commission error. You can see that big yellow bar there, where we're actually finding waterfowl that don't exist because of those mostly clumps of grass and dirt that appear very similar to a duck at this approximately 1-inch scale. So knowing that YOLO is the algorithm that appears to perform the best when we're using expert labels, or at least the best labels that we can derive. They were created by those trained biologists. YOLO performed the best, and we know that the 8-class structure is at least not, we don't have evidence that it performs acceptably. And so moving on from there, we wanted to start looking at the crowdsource data to say, okay, well, we can't keep an army of biologists labeling these data in perpetuity into the future. And so we're looking at using the crowd to do this. And there's another side to this that I'm sure you'll hear about next year from Rowan or the year after that, where we're part of the reason that the service likes the crowdsourcing idea is that it becomes an outreach activity. And so there's actually, Rowan's developed some educational materials to use in schools. The ones for a college course are already up on the Aspire website and downloadable if you're ever interested in offering a workshop or in running a class or a workshop doing this. And we're still working on the ones for grade schools, but it becomes an outreach activity. So we have these couple 100,000 labels. Well, that's, a bunch of people that have been exposed to the idea of inventorying waterfowl, why we inventory waterfowl, and how we do the data science to try to actually do it. And so there's a couple reasons to think about crowdsourcing, but the one that is important today is that it's by far the most affordable way to get a lot of labels, and we need a lot of labels, probably in the millions eventually, to be able to do this nationwide the way that the service is thinking about. So we took our expert labels and our crowdsourced labels, and we put them through YOLO, being the algorithm that performed the best with the expert labels. And we wanted to look at the effect of pool size and how it compares to the expert labels at the 1 and 3 class levels. Remember, we only have 3 class for the crowdsourced data. And so let me move this bar here so I can, what you can see here is it doesn't do quite as well. So what we're looking at is all labels. So in this case, we're taking the entire crowdsourced label set from label box, which is about 20,000 labels, and we're exposing all of them to the algorithm, and we're validating against the expert set. And this is what we get. So it's, instead of, a total classification accuracies in the 90s, we're down to 82%, but we're actually seeing more of the birds out of the imagery. So we are labeling 88% instead of 80% of the waterfowl in the image, but we're erroneously labeling some non-waterfowl as ducks, quite a few in this case, when we do the single class. If we do 3 class, we're actually able to label more of the waterfowl in the image, but again, our total classification accuracy is pretty low because now we can swap between those 3 classes. But not incomparable to the expert data set. One of the big things that you have to think about when you're doing this kind of thing is thresholding the confidence intervals. So the labels that come out of a neural network come out with a confidence threshold, a 4-digit number between 0 and 1 that indicates how much support that net sees for that label. And so how you threshold them will dramatically change your results. And so this is an early effort at trying to look at the effect of those thresholds. And so if you look at the orange line there, we're looking at the overall classification accuracy. If you look at the blue line, it's the waterfowl detection accuracy. So blue line is 1 class, orange is 3 class. And what you can see is as we move to accepting more and more labels as being waterfowl, our classification accuracy is declining. As we tighten up that threshold and have higher bar for entry to be considered a viable label, the accuracy is increasing. But as you can see, the orange there is already starting to make the turn and will decline in the other direction due to omission errors. So for a single class, with the optimal thresholds, we're able to get 92.2% of the waterfowl in the image using the single class crowdsourced data. And then if we look at 3 class for all labels, you've got in the gray there, goose detection accuracy. In the blue, the overall. In the orange is duck. And crane is flatlined there at the bottom, has 0. We only have a few cranes in the data set. And so that is our weakest training class by far. So with the 3 class, you can see we do a reasonable job with ducks, but not so good with geese or cranes because we don't have very many examples of those compared to the number of examples of ducks that we have. So key points from comparing the crowdsourced data to the expert data set. Remember, the expert data set's being is the validation set for the crowdsourced data. The crowdsourced data actually missed less birds. And part of the explanation for that is that we had about 20,000 labels in each data set. But if you remember for the expert data set, it's 20,000 divided by 18 in terms of pure original labels that represent new information to the neural net. Whereas in the crowdsourced data set, we've got 20,000 labels that are largely unique. And so we have a more representative sample of what different birds in different contexts can look like. So the crowdsourced data is actually better than the expert set at not missing birds, but it does also have more commission error than the expert data set. And so right now, the accuracy of the crowdsourced data is lower, although not by a huge margin, than the expert data, but it's in some way it is more robust on the omission error metric. And so we're focused now on making sure that we have better representation of crane and goose labels. and none of this results that I'm showing you uses any of the Zooniverse data, which is now in order of magnitude larger than the label box data set, and going to continue to grow. If you can, I should show you here in this image, if you can see on the right here, there's 3 actual ducks labeled, and then on the right hand side of that frame, you can see the things that are being ID'd as ducks. In that case, it's a clump of sticks and dirt. These are very high context environments. So what we're working on now is comparing our 18 experts amongst each other to just ask about how well humans can actually do this interpretation from this resolution imagery. We're looking at ways that we can refine our labels based on the crowd and who made those labels, right? So we can build up confidence intervals in individual labelers and try to understand how to prioritize labels based on who made them. We're working on the problem of the fact that these frames overlap and birds move. And so we're working with the biometricians at the service to try to understand how we can calculate availability bias and how we can understand true counts or make an estimate of a true count from what is a dynamic scene with the birds moving while the drone is passing over and birds appearing in adjacent scenes from each other. We are also working on the education side of this. So we're working with several environmental groups in the Southwest. The Audubon Society, they're listed here, to get them using our materials and engaging with Zooniverse. And there will be a component of Rowan's dissertation that actually measures the impact of engaging with this on those students and on their identity in STEM and propensity toward entering into a data science or another related field. And if you look on, I mentioned already on the Aspire website, under resources is a module for kind of geared toward college age students, introductory geospatial courses would certainly be appropriate, where students can go and learn about the elements of interpretation by interpreting in Zooniverse and contributing toward the project at the same time. The materials targeting grade school folks are in development now, but those will be up there once they are available. And then we're working on gamifying the crowdsourcing. So we want to reward people for engaging, and we want to reward people for doing a better job, and meaning creating better labels for us. And so we'll be on the lookout for if you want to come win the Drones for Ducks game. And Then it's not on here, but I'll just mention that, you know, we're working on, the goal here is to have this system be automated. So we are building a web-based architecture where we'll be able to take in new sets of imagery and spit out new sets of labels. But the other part of that is being able to take in new labels that from the crowd and have a feedback loop to the crowd to prioritize what we're asking the crowd to do based on what we need. So for example, I just told you we need more ducks and cranes. At a simple level, it could be like that. By class, we can then show more imagery with ducks and cranes in it to the crowd, or we can reward them for ducks and cranes more than we reward them for ducks, or for cranes and geese more than we reward them for ducks. Things like that. And then I hesitate to do this, but I have a 3-minute video that I think explains the project fairly well. You guys just start waving your hands if it is not coming through for some reason on your end. It worked a second ago. Hold on.
Did you see the comment to enable content in the upper right corner?
I did not see that. Thank you. Enable.
It's up above your slides.
Yeah. I'm just. I don't see the enable content button under more.
Oh yeah, go back to the editing view. There.
Ah, thank you. I don't know if I ever would have got there on my own. All right, try this one more time. There we go.
The goal here is to collect as much aerial imagery of ducks as possible to build a training data set so that we can identify ducks from a large image data set in the future.
And what we found is we started really high yesterday, around 60 meters, and then we dropped to 50, 40, 30, 20. And we got to 20, and it didn't bother any of the ducks, and so we figured, let's just try 20 today and see if that altitude would cause a waterfowl to spook or fly or get agitated.
Some of the ducks following the geese. There goes the duck.
Oh man. All right, so 20 meters is too low.
We're gonna get some birds in flight.
We went for 20?
So it's a learning experience out here. We haven't really been flying drones over ducks, or at least we haven't. Not many people have, I guess. And there's not a well-known parameter for don't scare the duck flight altitude.
So from a very practical and applied perspective, what we want to do is improve the accuracy and the affordability of how we count ducks on refuges. And that's important because we want to know how many ducks we have and what species composition we have, so we can make the right amount of food and the right type of food for when they come in. And that builds populations for just people to come and view them, photography, and for hunting communities. So, you know, refuges are really important for waterfowl. That's our history, that's our future, and we want to improve how we manage them. And this is a big step towards doing that.
One of the objectives is to get a good variety of species so that Jesse will take that information and try to train algorithms to identify the different species from the imagery that we're collecting right now, So we want to find a raft of ducks that has a good mix and fly those, and that'll be used as training data for our models and algorithms.
The counts that happen in the past and still happen today, there's two prominent ways. One of them is from the ground, so people will come to a wetland unit and bring a scope or a pair of binoculars, and they'll start counting ducks, and they'll say, okay, you know, there's 20 pintails here, there's 30 redheads here, there's 100 mallards here, and you've had big expanses of ducks. Then you'll do some estimation. So you'll say, okay, I count 50 mallards here, and I see a whole bunch, so I'll go 50, 50, 50, 50.
We're doing an airborne method, right? And as a foundation, you're getting a primary data record. So regardless of any of the other science we can do with that imagery, you have a data set that actually shows you how many ducks were there. What we're trying to do is take the next step and use machine learning to actually detect those ducks, figure out what kind of duck it is, and produce an automated interpretation and report of it. We have to be working with the people that actually have problems that are real and tangible and that they're faced with in their daily jobs to make the problems we're solving relevant to the world.
All right. So I just, that's all I've got for today. I'm happy to answer any questions about the program and what we're working on. And there's a few other adjacent activities that I'd be happy to elaborate on too. But thanks for taking the time.
Thank you. This was a really interesting talk. We do have some questions in the chat. So I'm going to read them off and you can answer them, hopefully. Okay, so
I'll try.
The first one, can you talk about the UAS you're using for this work and why you chose it?
Yeah, so all of the imagery that you saw today was collected with a Mavic Pro 2. And the reason it was selected is they are cheap and small and very easy to operate, and they have a nice 1-inch CCD Hasselblad sensor on them. So the logic there is the cheapest way to get the best sensor in the air you can. And we want the Fish and Wildlife Service to be able to do this. We actually started out, and we have a lot of imagery collected with an EB+, because we can cover a lot more ground with that. And it's got a nice 1-inch CCD 20 megapixel sensor as well. They're quite a bit more expensive. Instead of $2,000, they're 25 or so. But the issue became that the fixed wings really disturbed a lot of waterfowl. They're harder to take off and land, but they also scare the birds. They see it as a bird of prey. And so rotary wing actually is much less triggering for the waterfowl, and the less they move, the easier they are to get an accurate count.
Okay, that's interesting. Okay, so the next question from Patty Gaffin. What time of year are the images collected? Are they collected to avoid spring nesting birds?
They are collected in the fall migration, northward migration. So all of this imagery, I forget the exact dates, but is in the October, November, December timeframe. And that tends to be here in New Mexico when we're targeting them, is when they're on their northward migration. And I'm not a wildlife biologist or a bird person. But that's when I'm told is the best time to observe the widest diversity of species in high concentrations.
Okay. Can you expand on the federal UAS ban you mentioned? Any likelihood of it being lifted?
I can't answer that last part. One would think that there's a lot of motivation for it to be lifted. I know that a lot of folks at various DOI agencies are very frustrated by this ban. The ban is universal. It's just federal land. You're not allowed to operate UAS over federal land right now. I mean, military bases are an exception, but DOI land, I should say. So that includes BLM, Forest Service, Fish and Wildlife Service, refuges, all of those. And my understanding from the service is that they are not only now banned from conducting flights, but I think because over the past couple of years, a lot of people got creative, they are now banned from participating in the organization of flights. Like they're not supposed to be involved at all. So I really can't say, what's going to happen going forward. I know the original concern was motivated by Chinese manufactured drones, DJI, but the ban is universal.
So I'm sorry, Chris, if I could just to clarify, so it's universal, not even the so-called blue list of UAS are allowed for these flights?
Not according to the Fish and Wildlife Service, but they tend to be, I'm not sure if they're the most up to speed. They are not allowed to fly anything.
Wow, wow. Okay, thank you.
If you find out different, I would love to know, and so would my collaborators at the Fish and Wildlife Service.
Okay, we had a comment from Zach Edwards. He said, cool research, Chris. It will be interesting to see how this evolves as the labels are increased and refined. Okay, next question from Emiliano Salazar. Flight planning, time of day, is it due to the bird schedule? Shadowy early morning, can shadows possibly be used to help the algorithm?
Certainly, inherently the shadows are being used by the convolutional neural net because they're in the label. The timing in our case is about bird behavior. So we were flying in the morning when the birds tend to be sitting on the water feeding, and they tend to take off and leave late morning to move to their next spot. And so the timing in this case is about the birds. And so we normally, would keep things at low shadows. In this case, we don't really have that option. So we're flying, I think between 8 and noon, roughly.
Okay. Does anybody else have any other questions they'd like to ask?